equal to 7.5 times 10 to the power 3 plus by 60 minus 10 times 20 times 50. 50 times 10 to the power 3. Let me do it again. So 60 minus by 10 times 20 times 50 plus by 75 power 3 is equal to 575. Right, 57.5 times 10 to the power 3 millimeter cube, or 57.5 times 10 to the power minus 6 meter cube. Right, so the shear stress at point B, right, so this is equal to Vy over Izz, right, so this is multiplied by 57.5 minus 6 divided by 0.02, right, so 57.5 power minus 6 divided by 0.02 is equal to 2.875 times 10 to the power minus 3 Vy over Izz. Now we cannot make the assumption that A is going to be the same. It's always point B. Okay, I don't know. Okay, so we're going to calculate at the centroid again. Okay, we calculate the Q at the centroid. Right. So again, so we know that this is our width and this is our depth and this is our YY. Okay, this is our YY. So now we're going to find the shearing stress at point A using thick wall now, right? Analysis. And we know that the thickness now is 60 millimeters. Okay, or 0.06 meters. So the Q at point A is going to be twice the Q of point B, right? Why twice? Because you have one here, right, which stops at here, and then you have the other one over here, right? And next, we just need to find the first moment of area of this, right? Which is plus the width is equal to 60. The depth is equal to 60, right? Because 120, and then the Y bar is 60 divided by 2. Okay, so twice of Q at point B is equal to 57.5 times 10 to the power 3 plus by width 60 times 30 is equal to 108 times 10 to the power 3. So this will be equal to 2 times 57.5 power 3 plus by 108 power 3 is equal to 223 times 10 to the power 3 millimeter cube, or 223 times 10 to the power minus 6 meter cube. Let me do it again, okay? 2 times 57.5 power 3 plus by 108 power 3. 2233 is 60 times 60 times by 30, 108. Okay. So 2 times 57.5 power 3 plus 108 power 3. 223. Yep. Okay. So now we calculate the shear stress at point A. So V Y over VZ. So I got all these wrong also. Come on, Eugene. I do apologize. Okay. So this is also VZ. Over IYY. This is also VZ IYY. Okay, so VZ over IYY now is equal to 22 2 to 3 times 10 to power my 2 to 3 times 10 to power minus 6 divided by the thickness, which is equal to 60 times 10 to power minus 3. Okay, so 2 to 3 power minus 6 divided by 60 power minus 3 is equal to 3.7167 times 10 to power minus 3 VZ over YYY. Okay, so now come back to analysis again. The shear stress at point A is equal to 3.7167 times 10 to power minus 3 VZ over IYY. Then the shear stress at point B is equal to what? 2.875. So it's lower now. Can you see that? Right, 2.875 times 10 to power minus 3 VZ over IYY. And the shearing stress at point C, which is the lowest, I hope. Yep, 750 times 10 to power minus 6. VZ over IYY. Okay. So from here, we know that shear stress at point A is the location of maximum shear stress, right? So this will be equal to 75 times 10 to power 6. So this will be equal to 3.7167 times 10 to power minus 3 VZ over IYY, right? So we have VZ over IYY will be equal to 75 3.7167 power minus 3. Hey, 75 power 6 divided by 3.7167 power minus 3 is equal to 20.179 times 10 to the power 9 Newton per meter squared. So what you can see down here, right? At point A, now the centroid, right? The centroid had the what? Maximum shearing stress. It's different by before, and this is only us, right? Changing the direction of the shear force to be in VZ. So that's why you have to check and check and check in this, okay? Now, like earlier we said, you know, I did not ask you to check, but in my marketing scheme, I check. It is for this reason. And I want you to have this habit, because in 3E05, which is the next course you're going to take after this, it's the same thing. You have to calculate where or find out or investigate where the maximum shearing stress is, okay? So now from here, we now know that the shear stress, okay, come on, shear stress at point A is equal to 75 times 10 to the power 6 Pascal. The shear stress at point B now, which we can find, so shear stress at point B is 2.875 times 10 to the power minus 3, and then multiply by 20.179 times 10 to the power 9. So this is equal to 2.875 power minus 3 times by 20.179 power 9 is equal to 58.014 times 10 to the power 6 Pascal, right? And shear stress at point C, right, is equal to So at point C is equal to 750 times 10 to the power minus 6. 20.179 times 10 to the power 9. So this is equal to 750 power minus 6 times 20. It's 15.134 times 10 to the power 6 Pascal. Okay. Right. So this is a interesting problem, isn't it? It combines thick wall and thin wall. Now we are going to look at another example. Okay, we're going to look at another example. So this example, okay, is in your homework. Okay, it's your homework. So let's go to your homework. I'm going to copy. So this is on Avenue to Learn already. Okay, by the way. Okay, so let me go to your homework. Anyone, any question while I look for your homework? Anyone? Okay. So this is your homework. So let's look at this problem now. Okay, let's look at this problem. I'm just going to calculate the first moment of area. Okay, I repeat again. I'm just going to calculate the first moment of area. I'm not going to solve the problem. Okay, but I'm going to start you on in thinking how to solve the problem. So this is example number 3. Or example 4, sorry, the one before, yeah. So example number 4. Okay. So we have a extruded aluminum, right? We have an extruded aluminum. Hold on, let me string this to size first. Okay. It has a uniform thickness of 1/8 inch. Knowing that the vertical shear is 2 kilopounds of force, determine the corresponding shearing stress at each of the 5 points. Okay. So I'm not going to bother about finding the first moment of area. Sorry, the second moment of area. That is straightforward. Is the first moment of area that is going to be very destructive? Yes or no? Okay. So we're going to start from here. Okay. Yeah. Let me get a bigger diagram. So you can. Oh, this is way too big. Way too big. So the thing about first moment of area is you have to construct the shear flow first. If you cannot construct the shear flow, you don't know what area to take. Okay, that's why constructing the shear flow and applying rule number 5. Okay, rule number 1 to 5, they're all important. Okay, we're going to apply rule number 5. So rule number 5 say the web controls the flow direction. Yes or no? So the web for this case is at the center, right? Because the center one is continuous. It goes from the top and goes to the bottom. So you are going to construct your shear flow over here. Okay. Okay. So these are your Q. Right? Okay. Okay. So we know that we have the problem says that this is our Vy. Right? Now, in order for the flow the web to have that flow, it has to come from somewhere, right?